moi, c'est pas un problème pour des questions en français. Donc, j'invite des questions en français ou en anglais. Et aussi, j'aimerais prendre un moment juste pour remercier Aline, aussi Belana et René pour nous avoir aidé et invité de donner la présentation d'aujourd'hui. So today I'll be talking about something I think is a little bit different for our annals, but we'll be talking about air pollution, but there's a strong component of climate change research in the projects that I'll be presenting today. And specifically, what the goal is, you want to understand how meteorology and climate interact with pollution emissions to influence air quality in Quebec. So this is a very collaborative project. And so you can see here that specifically Helene and Alana have been involved in this project, as well as a number of researchers from my group, as well as from James King's group at University de Montréal. So, super. All right. Donc, I'd like to start simply with a really important notion for my talk, which is that atmospheric pollution kills. So we're talking about a major public health problem, even in Canada. And so we estimate about 14,000 deaths each year are caused by exposure to air pollution. And when we talk about air pollution, it's not just one thing. It's in fact quite complex chemically. So we have particles, ozone, nitrogen oxides. There's also arsenic, other types of metals as well too. And all of these contribute to poor air quality. In this talk today, I'm really just going to focus on particulate matter, so PM 2.5, so these are fine particles. We actually do research on a large range of different pollutants specifically for this project, but it's just too much for 50 minutes. So I'm just going to focus on the question of fine particles for today, and then Meg will be talking a little bit about volatile organic compounds. So what are these fine particles? Well, I'll be talking about PM 2.5, and so technically these are particles that have a diameter of less than 2.5 microns. And so just to give you an idea of what that size is, what we can see here is a human hair, so it's about 50 microns in diameter. And so the PM 2.5 particles here are represented by these little pink spheres. So we can fit 20 of these PM 2.5 particles in the diameter of a human hair. So this is a problem for air quality in Quebec. And so if you go on the Environment Canada website and it says, oh, okay, there's some sort of air quality warning, it's probably because of fine particles. And also this is a global problem as well too. So there's millions of deaths each year, premature deaths each year that are caused by exposure to particulate matter pollution. Normally, I focus really on the air quality aspect of it and the health aspect of it, but I do want to take a step back and just mention quickly, of course, when we're talking about fine particles, these are also known as atmospheric aerosols. And so in the climate community, we often talk about aerosols because of their important climate effects, because aerosols, of course, interact with shortwave radiation by scattering absorption. And also there's an indirect effect on climate as well by altering cloud properties. So while our focus is really on health, there is actually an important climate aspect to this research as well too. So where does this pollution come from? Where do these fine particles come from? And really there's a lot of complexity when we talk about sources. So we have things like cars and transportation, forest fires, of course, are a big problem here in Canada. Certain industries emit particulate matter, and also there's a lot of kind of unexpected sources as well too. So for example, cooking. So we like our bagels in Montreal, we like our wood-fired pizza, but those are actually big sources of particulate matter pollution as well too. So they're both anthropogenic and biogenic sources, so natural sources of these fine particles. And in addition to sources, transport and long-range transport is an important contribution to particle PM 2.5 in Quebec. And so what I'm showing right here is the result of a study we did where we essentially modeled the transport of pollution into Quebec using meteorological data. And what we found was that periods of high PM 2.5 concentrations in Quebec are correlated often with air masses that are arriving from southeastern Ontario and from the Midwest of the United States. So essentially, we have air masses that are coming from these regions that take the emissions from Detroit, from Toronto, and then those emissions are carried to Quebec, and we can see those higher PM 2.5 levels in the province. So yes, we have local sources, but we also have this transboundary contribution as well too. So, I doubt there's any chemists in the audience, so I'm just going to quickly do a crash course in atmospheric chemistry and the atmospheric chemistry of aerosols. So it's only one slide, so it won't take too long. But in this slide, it's actually, I forgot to put the reference here. This is actually from Daniel Jacobs' textbook, Introduction to Atmospheric Chemistry. And what it summarizes here is the processes that are the sources of aerosols or particulate matter in the atmosphere, and then the processes that are the processus de dépôt, so the deposition processes. for particulate matter. And so, of course, we have things like dust, windblown dust. We have emissions from tailpipes, so the soot you see coming out of the tailpipe of a car. And these are what we call primary particulate matter, where the particles are emitted directly into the atmosphere. But in addition to this primary particulate matter, we also have something called secondary particulate matter, so secondary PM. And that follows the process that's shown here, where initially we have emissions of gases, so it could be sulfuric acid, ammonia, volatile organic compounds, which Meg will be talking about later. And then these gases are transformed in the atmosphere to produce particles by nucleation. And then these particles, which tend to be quite small, nanometric, will grow quickly in the atmosphere by condensation and coagulation to form fine particles. And so we have these two types of sources. So we talk about transport, we talk about fires, but in addition, we can take those sources and we can categorize them. We have primary sources and we have secondary sources. And they both are actually important for explaining the total amount of PM2.5 that we observe in the atmosphere. Okay, so now I want to talk specifically about the project that we're working on. And I'm actually in the process of rebranding this project. So I'm calling it now the Atmospheric Chemistry Transport and Emissions Project. And to start off, I just have a very simple schematic here of the way I would normally think about air quality, sort of the traditional way to think about air quality and health. And that's, we know we have emissions of air pollution, and then those emissions are transported or dispersed by winds. And so these emissions in meteorology interact to determine essentially the air quality in a city like Montreal. But we can take a step back and we can ask ourselves, okay, what are the things that drive emissions? What are the things that drive meteorology? And on the emissions side, we know that public policies and technological development will influence emissions. And so emissions are changing from one year to the next because there's more stringent, more strict laws, or maybe there's new technologies for treating emissions from certain sources. And of course, on the other side, as everyone in the audience knows here, we know that climate change is driving changes in meteorology as well, too. And so if we take a step back, okay, really the fundamental drivers here are policy and climate change. And so this project, ACT, the goal is to really look at, okay, how do changes in climate and public policy interact to determine what the future of air quality will be in Canada? And so this here, and of course, when we talk about public policy, it's not going to just affect emissions of air pollution, but also the emissions of greenhouse gases as well, too. So the way this project has been structured is we initially started with financing from the MELCCFP. That's what I'm calling here phase 1. And actually that financing is going to continue until 2027, but in a new framework because it's being used with funding from NSERC from an alliance grant. So there's a bit of a transition we're going through right now where we're going from a model where we're just funded by the MELCCFP to a project now that is now jointly funded by the MELCCFP and NSERC. So that's nice because it does give us more opportunity for training and outreach activities and organizing workshops and things like that. So it's actually a nice. So I'm really excited to be going through this transition right now. In terms of the people involved in the project, in addition to myself, there's also Audrey Smarziassi at Public Health at University of Montreal, James, who's in the audience here today, Marianne Hatzablu at University of Toronto, Laura Monet at University of Victoria, and of course, Aline at Bonn. So the different axes within this project are summarized here, including some of the major deliverables. I don't want to get into all the bullet points here for the deliverables, but I just want to highlight the subjects we'll be talking about today. So within the first axis is focused on apportioning the sources of PM2.5 and VOCs. And so this is really looking at current conditions and saying, okay, how much of this fine particulate matter is coming from burning of wood? How much is coming from vehicles? And asking the same question for volatile organic compounds. Okay, of these pollutants, how much are coming from different sources? And so I'll be talking about that a little bit today, and then Mega will also be talking about it as well. In the second axis, we're looking at climate air quality interaction. So how do future changes in climate impact air quality? So is there sort of a climate penalty where we're going to see climate change is making air quality worse, or maybe there's some sort of negative feedback loop where actually climate change is improving air quality? Unlikely, but we don't know. And so this is part of this work includes just looking at regional climate models and assessing the climate change signal and some key meteorological parameters. And Yoandy will be presenting about that today, and then also projecting future air quality. So you're doing a projection of future air quality a little bit like we project temperature, but in this case, projecting the concentrations of fine particles, PM2.5, or other pollutants. And I'll be talking about that at the end of my presentation today. There's also a third axis where we're focused more on emission inventories and developing scenarios for different levels of emissions in the future. So, for example, what are the emissions if the vehicle fleet is 100% electric. And that is something that's being worked on by Marianne Hatzopoulou and Audrey Smarzassi. So I'm not going to talk about that today, but you could always invite them to Oranos to give a talk about that at a future date. So I'm going to talk a little bit about the source apportionment of fine particles using PMF. In terms of PMF, this is what we call a receptor model. So the idea is we're going to use data from a monitoring station, and then using that data, we're going to attempt to model the sources that contribute to the pollution at that site. And I'm not going to get into the technical details of PMF right now. Mega's going to talk about that a little bit more in her presentation. But really quickly, it's like PCA, so principal component analysis, but the principal difference is unlike PCA, we're going to constrain all the results to be positive. And we do that because you can't have a negative concentration of a pollutant in the environment. That doesn't physically make sense. And so for the input to the PMF algorithm, what we use are the concentrations of different pollutants. So we look at the PM 2.5 and we look at the dust in the PM 2.5, the soot, the metals, the salts, all the different components that contribute to the total PM 2.5 mass. And we use that data on composition, and we basically deconvolve it into two types of factors. We have, well, not factors, but two types of matrices. So we have the factor profiles here and the time series of factors. So I'm going to use this word factors, but what factor really means is source. And so a factor profile, this is kind of like the chemical fingerprint of a source, because each source will have certain ratios of organic pollutants that are emitted, sulfate that's emitted, soot that's emitted. And then we also get the contributions of those sources. So that's the time series of the factor. So the idea is we have all this data resolved in time for the composition of the PM 2.5. And from that, we can identify the sources by their chemical fingerprints. And then we can also determine the contribution of those sources to the total amount of PM 2.5. So we applied this method to monitoring data from two stations. One station in Montreal, in the east end of Montreal, which is indicated by this red marker here. And then also one station that's located in the southwest of the province near the border with Ontario called Saint-Innocent. And we used data from 2014 to 2016. And we used, I won't get into the details of all the measurements used, but essentially we're looking at data on elements, metals, ions, organic carbon, soot, and also certain organic molecules as well that are good tracers for certain sources. So this is essentially the output of the PMF analysis. And so this is where, this is where for a chemist, it's quite interesting to look at all this data, but I realize it's maybe a bit overwhelming for most people. And essentially what we're seeing here are these kind of chemical fingerprints. So I'm not going to discuss all the figures here, it's too much, but I just want to highlight a couple of results that are quite interesting. So for example, for wood burning, we have here the percentage of each chemical compound that comes from wood burning. And what we can see here, for example, is for wood burning, 100% of the levoglucosan is attributed to wood burning. And this makes sense. So levoglucosan, it's actually kind of a sugar that comes from burning wood. So when you burn wood and you get this smoke, one of the major components of that smoke is this sugar called levoglucosan that just comes from the breakdown of wood. Also, for example, we see salt here. And actually what we think this is road salt. And of course, the salt contains a lot of sodium and a lot of chloride. So what we can see is that there's certain components of the PM 2.5 that are specific to certain sources. And the PMF analysis also allows us to attribute this fine particulate matter to a variety of different sources. So we have contributions from wood burning and salt and organic aerosol, ammonium nitrate, mineral dust, ammonium sulfate, et cetera. And here I just want to distinguish these primary sources. So wood burning and salt, which are emitting particles directly into the air. And salt, this is, like I said, is road salt being picked up by vehicles, versus the secondary sources, organic aerosol, ammonium nitrate, and ammonium sulfate. So organic aerosol, this is just organic material that's been oxidized in the air. And then ammonium nitrate, ammonium sulfate, it's a little complex, but these are essentially products of oxidation of SO2, so sulfur dioxide, and NO and NO2. So these are salts that are produced by these secondary chemistries that I just discussed. So here, what I'm comparing is the results from Montreal and Saint-Innocent. So essentially on the left here, we have this urban site, and then we have this more rural site here. And what we see is, of course, in the urban site, the concentrations are higher, but there's a certain concentration also in the rural site as well too. And then we've plotted both the total concentration as well as the contribution from the different sources as a function of the season. And so, for example, in Montreal in winter, what we see is that the concentrations of PM 2.5 are the highest, which is already well known. And what we also see is there's this larger contribution from wood burning, which makes sense because we have residential burning. People use wood, at least in 2014 to 2016, people used wood to heat their homes. And so we see a higher contribution from wood burning to the PM 2.5. We also see a higher contribution from salt because we put salt on the roads. And when the cars go over that salt, that gets kicked up in the air, and we can see that as well in the PM 2.5. I also want to highlight here for summer, we have the stronger contribution from this organic aerosol. And so this is the organic fraction of the particles. And so the main takeaway point here is really, okay, we're already starting to see, okay, temperature is influencing the PM 2.5 concentrations, okay? During winter, there's certain sources that are more favored. In summer, there's other sources that are favored, okay? And so so this is kind of a little bit of a sneak preview of what I'm going to be showing later, where we see that, okay, temperature is this important factor that's really driving changes in the sources and the concentration of PM 2.5. Okay, so that's the first result I wanted to show. I also want to talk a little bit about the second part of the project, where we're projecting future air quality levels. And so to do this work, it's not receptor modeling we're using, but rather chemical transport modeling. And so essentially a chemical transport model is not dissimilar from a climate model. We take the atmosphere, we divide it up into a 3D grid, and then each one of these cells is essentially a little chemical reactor. And so in that cell, we're going to simulate emissions, transport, chemistry, deposition, and other processes that are important for predicting air quality. The difference, I think, between a chemical transport model and a global climate model or regional climate model is we're really going to go more deeply into the atmospheric chemistry and parameterizing that chemistry, because that's really necessary to have a good representation of air pollution. So the model that we're using specifically is the geochem model, and the geochem model is widely used by different university groups, and it's a model that's run on the Narval cluster that's hosted by Québec. And in the model, we're using well-established inventories for emissions from cars, from fires, et cetera. We also are running simulations for this period from 2012 to 2016. And we have a high-resolution domain, which you can see here over Northeast Canada, which is nested within a global simulation as well. So we have the ability to do more focused simulations as well as global simulations as well, too. And then in our work, what we like to do is we like to do these toggling, where we essentially turn off emissions from different regions. So we turn off emissions in Quebec, then we turn off emissions in the rest of Canada, and then we turn off emissions in the United States. And the idea is by doing these toggling experiments, we can quantify the emissions from each region. So here I'm showing the results of this toggling experiment, where you see the contributions to PM 2.5 from Quebec, from the rest of Canada, and from the United States. And this is the top row here. What you can see is the absolute difference in the contributions, and then in the bottom row here, what you see is the relative difference in the contributions to PM 2.5. So I think it's easier just to focus on the bottom row here. And what we can see is if we turn off the emissions in Quebec, we get the strongest reduction in the St. Lawrence Valley right here. And that makes sense because that's where the emissions are. This is where people live, so this is where we have the strongest emissions. On the other hand, if we turn off emissions from the United States, I actually see kind of a similar effect in terms of the scale, the magnitude, but it's much more diffuse. Okay, because there's basically all these different sources in the United States which are getting transported by the dominant winds into Quebec. And so we see there's also a pretty important effect that's due to this transboundary contribution. And finally, for the rest of Canada, it's similar to the United States, except the size of the contribution is smaller. So there's this kind of diffuse but smaller contribution to PM 2.5 levels in the province. And so what we do is we look over these coordinates here and we average these results. And these coordinates correspond to roughly the southern third of the province. What we see is the contribution from Quebec emissions is equal almost to the contribution from the United States of America. And then there's also an important contribution from the rest of Canada, but it's smaller than the contribution from the other regions. So what this means is, we take a deep breath today and we are exposed to this pollution, roughly a third of that pollution is coming from the US, and another 15% is coming from the rest of Canada. And at a policy level, what this means is our ability at the provincial level to improve air quality is somewhat limited. Because yeah, we can reduce emissions here, but in the United States, it's going to be pretty hard to reduce emissions, as a local government, or a provincial government. Especially if Donald Trump is the next president of the United States, it's going to be even harder to control those emissions across our borders. And so then we also dug a little bit deeper into this transboundary contribution and these results in a second paper. And here I'm going to get a little bit more into the chemistry details again as well here. And what we're seeing now, again, is the contributions from the US, from the rest of Canada and Quebec. But now I've broken it up by these components of PM2.5. So here I've got the secondary organic aerosol and the contribution to ammonium sulfate. Again, the identity of these compounds is not really important for the talk today. What this is important here is that these are both secondary types of PM. Okay, so these are produced by oxidation, processing in the atmosphere. And what we can see is that these have large contributions from the United States. So fundamentally, what this means is that the emissions in the United States that are problematic are not the primary emissions. It's the secondary emissions. So the emissions of gases, which are then processed in the atmosphere during transport to form particles. And that is what we're seeing here in Quebec, measuring in Quebec, is this secondary particulate. So for the last couple of minutes, how much time do I have? Oh, I'm doing okay. I got 10 minutes maybe or so. Okay, sorry, I'll slow down. Here. Which is good because this is the most hardest for me to present. So the last part of my talk, what I want to talk about is how climate change is going to influence this transboundary pollution. So clearly, emissions from the US in particular and from Quebec influence air quality in Quebec. And with climate change, and I'm showing here some results from climate simulations that were taken from the IPCC report, we know that there's going to be increases in precipitation, increases in temperature. And so those for sure are going to affect this transboundary contribution. For precipitation, especially wet deposition is very important. So essentially when it rains, when it snows, that's going to take pollution out of the atmosphere. So with increasing precipitation, we may have more wet deposition, and that may actually reduce the transboundary contribution. At the same time, we know that with temperature increases, that essentially increases the speed of chemical reactions. So I mean, the secondary formation pathway will become more important with increasing temperature. So that's just some hypotheses essentially about how climate change is going to affect this transboundary pollution. And we have really, at the beginning of this work, we have no idea. Is it going to increase or decrease with climate change? And of course, winds are important too, and Joandy will be talking about that as well later. So to model the transboundary contribution, we're actually going to use an approach that's divided into 3 steps, where in the first step, we're going to perform geochem simulations. So using the exact same approach or almost the exact same approach that I already showed, where we have meteorological data that is used to drive the geochem model. And then we're going to use geochem to simulate historical concentrations of pollutants. So ozone, PM2.5, and other pollutants as well too. And then we're going to use these results, so the historical concentrations and the meteorological data, to develop what we call an emulator. Okay, the emulator is essentially a simplified model for predicting air quality in Quebec. And the emulator, it is quite simple. So it is it's just a multilinear regression where we take the concentration of a pollutant, in this case, the concentration of PM2.5, and we do a linear regression against multiple meteorological parameters. There's a little bit more to this than just a simple multilinear regression, where we also take into account synoptic effects as well too. I'm not going to get into that in my presentation. I think I'll talk about it offline, but we're not just looking at local meteorological parameters, we're also looking at synoptic level parameters as well too. So I just want to say that is a level of detail we do capture in the emulator. And then once we have this emulator, we can then drive the emulator using regional climate model data. So the emulator takes the regional climate model data and then produces projections for pollution, including fine particles, ozone, and nitrogen oxide. So I think Robin also talked a little bit about this as well when he presented a couple of years ago. So here, obviously this is where Aranis's role becomes very important because we need their expertise for understanding the climate model data and using the climate model data correctly. So that's really the key role that Aline and Balana are playing within this portion of the research project. So the question is, okay, what climate model data are we going to use to drive our emulator? And this Venn diagram shows all the different considerations. that we used to select the climate model parameters. And so the first thing that, of course, is very important is that this has to be a parameter that's available in the climate model output, okay? Because we want to use the climate model data to drive the emulator. Second factor is also has to be used within GeoSchem, because otherwise we can't train the emulator using our GeoSchem output. And then the other factors that are important as well, too, is that we want to select climate parameters where the cross correlation is less than 0.8, because obviously if you have two parameters that are highly correlated, that doesn't really give us new information for the emulator. And then lastly, for practical reasons, we selected parameters that are spatially two-dimensional. I mean, there are certain instances where having a three-dimensional data would be quite interesting, but at some point it just becomes very difficult computationally to do this analysis. So if we take all these considerations together, we decided on the 7 climate parameters shown here. So we have temperature, RH, precipitation, pressure, surface level pressure, winds, and downward shortwave radiation. And so then we took this output from various versions of CRCM5, and we use that to drive our emulator. And specifically, the climate model data we're using is from CRCM5, and we're looking at 2 scenarios, RCP 4.5 and RCP 8.5. I guess I'll just add here quickly is that we do want to use the SSP scenarios as well too in the future, but because of data availability and timing, it wasn't possible yet. And then to kind of have an ensemble of results, we use CRCM5 driven by 4 global climate models. And then we use the output of the emulator and compare that between future and the present. And that allows us to estimate the changes in the pollution concentrations. Also, one other thing we can do with the emulator that's a big advantage of this approach is that initially we're going to train the emulator using the total PM2.5 concentration. But we can also train the emulator using PM2.5 from each geographical region. So the emulator can project the PM2.5 from Quebec, the PM2.5 from the rest of Canada, and the PM2.5 from the United States. And that allows us to use the emulator then to also evaluate transboundary contributions in the future. So here we're seeing the result of essentially the base run with the emulator. And what we're seeing here is the annual mean change in PM2.5 between 2080 and 2100 and 2006 and 2026. So it's the difference of these 2 periods that we're looking at in this figure. And what we see is across the whole region of Quebec, there's an increase in the concentrations of PM2.5 because of climate change. In this case, I'm showing the results from the 8.5 scenario. For the 4.5 scenario, it's really the exact same map, except all the concentrations are, well, the increase is reduced by 50%. So it's basically half the change. I want to emphasize here that this is really just the effect of meteorology on air quality. Okay, the emissions are fixed to 2010, which is our reference year. So we're not accounting for changes in emissions. That's something else we're looking at in the future, especially with Audrey and Marianne. But what we've done is really just isolated the effect of climate change on air quality. We can also look at the transboundary contribution. And so in this case, we're seeing the change in the contribution from Quebec, the rest of Canada, the United States. And what you see here, the big takeaway message is, okay, the change in the contribution from Quebec isn't much, not much from the rest of Canada either. But most of this change that I showed on the previous slide is coming from the United States. Okay, so we have this climate penalty, this increase in PM2.5, and that's almost 100% because of transboundary contributions. So we're going to receive more of this fine particle matter from the United States. Okay, so why is it that this contribution from the United States is becoming so important? And so this is a question that really shows the advantage of using this emulator, is that because now we can take the emulator and we can drive the emulator using each meteorological parameter individually. Okay, so rather than using all 7 at once from the climate output, we can just use the increase in temperature. We can just use the changes in relative humidity or precipitation. And so we drive the emulator with each climate parameter individually. And what you see here is essentially for most of these climate parameters, like winds or RH or pressure change or precipitation or downward shortwave radiation, there's really no change or no influence on the PM2.5 levels. And when we're projecting these PM2.5 levels out to 2100, it's really temperature okay, that is explaining all the increase we're seeing. Okay, so it's really the changes in temperature that are driving this projection to higher PM2.5 levels. And why is that? Well, I think there's two explanations. And one of which is that, when you look at the changes in the climate parameters, the temperature is, as you all know, it's the biggest change, So it's the delta for T is large, it's very certain between the different model configurations, and it's very homogeneous. You see temperature increase all across the province. And the other factor, I think, as well, is that we know that with higher temperatures, we're also getting a lot more, and this is getting into the chemistry, a lot more secondary aerosol formation. So with higher temperatures, these secondary processes speed up. So this oxidation of material from gases into particles is becoming more quick and more rapid. And so we have more of this formation of particles as this pollution is being transported from the United States. Yeah. Okay, so I think we're just going to leave it there because Mega's going to present next. I summarized all the conclusions here from my talk. And I think in terms of questions, unless there's a burning question right now, we can take the questions at the end.
Maybe one question.
Okay.
Again, explain the difference between the primary and secondary sources.
Yeah. So the difference between primary and secondary, primary is something where it's a source where the particles are emitted directly into the atmosphere. So the classic example is like the diesel truck with the tailpipe, and you look at the tailpipe and you see the black smoke coming out of that tailpipe. And so that's a primary emission because it's coming directly into the atmosphere. Secondary, it's actually emitted initially as a gas. So you have a vapor that's in the air, so no particles, and then there are chemical reactions that occur in the atmosphere that then transform those gases into particles. And so initially you have a vapor, but with time that vapor then starts to form nucleate particles and form small. And so that's the difference between the two sources.
Yeah.
Right. So if I do this correctly.
My name is Megha. I'm a PhD student in Dr. Hayes' research group. And thank you for setting up the good context of my project. Right now, I am studying the source apportionment of volatile organic compounds in Quebec. So the aim is to identify the various sources of these volatile organic compounds and how much these sources are contributing to the air quality in Quebec. So beginning with what are VOCs? VOCs are a large group of contaminants which are usually present and emitted as gases because of low boiling points. Certain examples of with chemical structures I have here on the bottom. So benzene, toluene, ethylbenzene, xylene, these are a few very easily found VOCs present in the atmosphere. We get exposed to these VOCs every day. We might not realize, but they're very easily present in our environment. They're used as fuel additives. They're present in paints, pesticides. As Dr. Hayes mentioned too, the cooking also releases a lot of VOCs in the air. Cleaning supplies has VOCs in the air. Certain perfumes, the distinct smells we have from a certain perfume or certain, you go out in the nature, the woods have a certain scent. All of those are because of VOCs. Other activities like printing, dry cleaning, all of these emit VOCs in our environment. So we are very easily surrounded by them. The current objective of the project is to, like I mentioned, identify and also quantify these emission sources of VOCs in Quebec. The main tool that I am using to do this study is called positive matrix factorization, PMF. The study period is from 2014 to 2016, purely based on the availability of data. And we're studying the spatial and temporal differences across 4 sites in Quebec. So these are the 4 sites, Parc Saint-Jean-Baptiste, which is present in Montreal. It is a large urban residential area. The second one here is Saint-Anicet, which was also highlighted in Dr. Hayes' talk, very close to US. This is an agricultural rural study site. The third one is Professeur. This is again a small urban area with agricultural land use. The last one here is Lemieux. This is a rural forested study area. And we see differences in our sources based on the land use and based on the population, based on the placement of these study sites. So that's where the position of where they are located comes into play. Okay, so the main tool that I use is positive matrix factorization. It is a complex model, and to explain it in easier words, we input our data, which is concentrations over our so various VOCs and their concentrations over our study period. And we also input the associated uncertainties. What PMF does is it tries to simplify it into two matrices. Like Dr. Hayes mentioned in his talk, the two matrices here are G and F. G being, so F is the species profile and G is the species contribution. To explain this better, I'm going to jump to the next slide. So this is our equation here. X is our data matrix with our concentration of our compounds. G is the, F is the species profile. So you see here, for example, I have a species profile that was given as an output in PMF. So this profile is called natural gas. And on the top plot here is the species contribution. So we see in the bottom plot, the contribution from the red squares, I'm talking about the red squares, contribution from propane and butane is the highest in this profile. And we know propane, butane, and ethane, all of these are associated with natural gas use. So this factor we call natural gas. And then we see how much this factor is actually contributing. So we see a good trend, a good pattern here with higher values in winter and lower in summer, which again makes sense because people are using natural gas to heat their homes and other things. So higher values of contribution we see from this factor in winters. So this is how PMF works, and this is the output we get. Coming back, so this equation here, the data matrix, is resolved into our species profile and their contribution. E here is the residual between the solution resolved by PMF and the actual concentrations. P here is the number of factors. This P is a user-defined value. And to reach to an optimal solution that makes sense in real life, the user plays around with P, basically. So we start with our knowledge of literature, the knowledge of the area. So for example, if I talk about Montreal, I know it's a big urban site. So transportation is, of course, going to be one of the biggest source. And then we know there are some refineries surrounding Montreal. So then refineries could be another source of these compounds. Then natural sources are also present in the air. So just by a general understanding, I know at least 3 or 4 sources. So that's how, that's where I would start with a value P equals to 4. And then we increase or decrease our P value and go through all the results or the PMF results and finally come to an optimal solution. There are various ways of finding what the optimal solution is. One of the key factors we study is object function, which is Q. So this big equation here is nothing but if you calculate the value for E, it comes out to be this term. So Q value is nothing but our residual upon our uncertainties. And when we plot the Q value over our P, we see a elbow plot, and there's a sudden increase or decrease in the value of Q. And that basically gives us an estimate of which is the perfect number of P to use for our analysis. Okay, so for this study, the data I have is downloaded from National Air Pollution Surveillance Program, which is NAPS. My study period is from January 1st, 2014 to December 31st, 2016. We have data from 4 stations across Quebec, like I mentioned. 16 to 46 VOCs were studied across all of these 4 sites. Samples were collected by NAPS once in 3 days or once in 6 days for a 24-hour duration. I also have wind data obtained from ERA5, which I use to associate my pollution with direction, where it is coming from. And then, like I mentioned, the key tool used for this analysis is PMF, which was developed by Environmental Protection Agency. And to reach to this optimal solution, various other factors like previous publications, Q value, all of this were taken into consideration. And then the monthly trends and the variation with the wind, the plots that I show are made using the open air package in R. Moving on to the results. So these are the 4 sites I have: Lemieux, Saint-Anicet, Les Somptions, and Parc Saint-Jean-Baptiste. 17, 17, 24, and 46 VOCs were taken as the input for each site. And these were resolved into 7, 7, 6, and 9 factors. If you look at the first 6 factors, they are common across all the 4 sites, which are industrial, biogenic, global background, natural gas, vehicular, and long range. Unique factors were identified at Lemieux, which was refinery, at Saint-Anicet, being refrigeration, Parc Saint-Jean-Baptiste, which was refinery. Another fugitive benzene factor was found here as well. And another interesting thing happened at this site was we saw the vehicular factor splitting into 3. And since this is the only largest urban, big urban site, it was expected that we will have a little more complicated results at this site. And that's what we got in our results as well. For this presentation, I'm going to talk about Les Somptions, but in our analysis, we have the results for all the 4 sites, but it's going to be repetitive and too much for a short talk. So, okay, this is what the PMF output looks like. On the bottom here, we have our input VOCs. So all the VOCs that I studied are listed here. The left axis here shows the concentration of species with blue rectangles. On the right here is the percentage of species. When I talk about the presence or absence of a compound in a factor, I'm talking about the red squares. And that's what I want you to follow. All the rectangular blocks you see here are the factors or the sources that we found. So the first one here is dominated by these compounds here, high concentration, high values of these red squares. And these compounds are freon, chloromethane, carbon tetrachloride, and dichloromethane. So halogenated compounds, all of these have atmospheric lifetimes ranging from months to years. So this we call as global background. PMF does not have 5 minutes. Okay. Also, the PMF does not define what this factor is called. It just mathematically resolves the matrices. But based on we call these tracer VOCs. The higher concentrations of certain compounds we find in each factor, based on that, we name the factors. So we see these compounds have higher lifetimes, so they're present for a very long time in the atmosphere, so we consider them a background. So this factor is called global background. The next one here is dominated by ethane and ethylene and propylene. These are both used as industrial and for manufacturing uses. So we call this the industrial factor. The next one has nothing but one compound, which is isoprene, and this is emitted by vegetation plants. So this we call the biogenic or the natural factor. The next one is dominated by propane and butane. So this again associated with natural gas, the natural gas factor. The next one here is acetylene and benzene, lifetimes ranging from a few days to a few weeks to a few months. So we are categorizing this a little below global background, so we call it long range. And the last one here has these compounds which like toluene, the substituted aromatics. These are found to be released from vehicles, so we call this a vehicular factor. So this is what we got for Les Somptions. Here I have a windrows for my study site. We see most of the wind is coming from the southwest. This will be relevant when I talk about pollution roses, like here. So we have all the factors here: vehicular, industrial, global background, long range, natural gas, and biogenic. Talking about vehicular factor, each sector of this circle, the length of the sector represents the frequency of the wind, and the color represents the concentration. So you see, longer the sector, more the winds are coming from that direction. And you see shades of red, that means more pollution is coming from this direction. So this vehicular factor is mostly coming from southwest. And if you remember the location of L'Assomption on the map, we have Montreal on the south, and we also have US on the south. So it makes sense that most of the vehicular concentrations are coming from that direction. Similarly, long range shows a similar pattern. I think I'm running low on time, so I'm gonna skip to the next slide. Here I have the monthly trends for factor contributions and the tracer VOCs. Tracer VOC, if you remember, was the 1 or 2 compound that was majorly present in a factor. So each red line represents the factor contribution. Each blue line represents the tracer VOC concentration. For example, if we have here, I have the biogenic factor contribution. Biogenic VOCs are emitted by plants, and the production and emission of isoprene and biogenic VOCs is highly dependent on temperature and sunlight. So we see a higher concentration in summer. This is the concentration of isoprene, and this is the contribution of the biogenic factor to total VOCs at this site. We see similar patterns between the factor contribution and the tracer VOC at all sites except for global background. This is for natural gas. We have long range, we have industrial, and vehicular. That was all for L'Assomption, but we have interesting findings at other sites also. Starting with the results for Parc Saint-Jean-Baptiste. As I mentioned, this was the only large urban site, so we have a little bit more complicated results here. We found 9 factors and a lot of VOCs. If you look at this particular factor here that I highlighted in red, has just one highly dominated species, and if you look what that species is, it comes out to be benzene. Why we are focusing on benzene is because it's a very nasty compound. It has health effects. These VOCs are also precursors, and they form secondary pollutants like Dr. Hayes mentioned, and are precursors for ozone production. So looking at this benzene factor, these are the contributions for benzene at Parc Saint-Jean-Baptiste. And this is the pollution rose. We see high concentrations coming again from southwest. And if we place this site on the map, which is here, we see Suncor refineries in the same direction as well. So probably these refineries are a good source of fugitive benzene. There are a lot of storage tanks that we see, and this whole area is probably part of the refinery. We have a little loading dock here as well. So high concentrations could be coming from leakage or probably from the refinery itself. And this associates with our direction, with our pollution rose as well. So this was interesting to see. Here I have the contribution of benzene from all 4 sites. I have the land use mentioned here and the mean concentration in the parentheses. So in all the 3 sites here, we see long range transport to be one of the biggest contributors, but at Parc Saint-Jean-Baptiste, fugitive benzene and industrial were bigger sources contributing to benzene. So yeah, that's the same thing. These are the 4 sites, and contribution to benzene is highly associated with the direction on the map as well. If we talk about the guidelines for concentrations. In Quebec, there's no annual guideline for concentration of benzene, but Ontario has a guideline of 0.45 micrometers per cube, and at Parc Saint-Jean-Baptiste, it exceeds by a factor of 3. If you talk about 24-hour guideline, Quebec does have a guideline of 10 micrograms per meter cube, which was only exceeded in 1 out of 182 samples. But comparing it again to Ontario, it has a very lower guideline of 2.3, which was exceeded in 20% of our samples. A similar case like benzene was also found at Lemieux, where this refinery was again associated with high concentrations here. This is for butane. Seasonality in ethane and propane with natural gas use was also found at all sites. So we see high concentrations in winter, low concentrations in summers with ethane propane concentrations. And that's it. So to conclude, unique factors were identified at Lemieux and Parc Saint-Jean-Baptiste, being the refinery mostly. Urban and industrial areas were found to have higher concentrations of natural gas uses, ethane and propane, mostly due to energy use, due to heating, transportation. Long-range transport was found to be the biggest contributor of benzene at Saint-Anisette and Lemieux, but at Parc Saint-Jean-Baptiste and Les Somptions, which are the more urban sites, fugitive benzene was the bigger contributor. And talking about all the 4 sites, the results that I don't present here, global background was found to be the biggest contributor to total VOCs at the 3 sites, versus the 3 vehicular factors combined were more contributing to VOCs at Parc Saint-Jean-Baptiste in Quebec. So that was it. Thank you.
Merci beaucoup, Patrick et Méga, pour ces très intéressantes présentations. On a le temps pour on a quelques minutes pour des questions. Est-ce qu'il y en a en ligne présentement?
J'ai déjà posé la question.
D'accord. Dans la salle? Charles?
I have a question for Mega. I was wondering if you could explain the difference between vehicular 1, 2, and 3 in the sources that you indicated. Like, what's the difference between the 3 of them?
Just a different tracer compound that we found. So here. So yeah, at other sites, all of these tracer compounds were found in one factor, so we called it vehicular in general. But here, because they have a lot of VOCs and a lot of factors, so certain VOCs might not be correlated well, and that's why we see a splitting. And it's just a different tracer for each factor, but all of those tracers come from vehicles. So we just call it vehicular 1, 2, 3. There's no other real difference.
All right, thanks.
Yeah, I mean, the other thing is the VOCs have different lifetimes in the atmosphere. So we think some of the different vehicle factors are like really local traffic, and some are maybe more distant traffic, because the ratios of VOCs will change depending on our distance from those vehicles.
And some could be from like vehicle, like gasoline, some could be diesel, so a different source as well.
Great, thank you.
Est-ce qu'il y a d'autres questions?
Avec question, je peux poser?
Yes.
So I like, Patrick, you comment on the limitation of the method that we use for the future climate projection, because it's fully related on statistical methods. So what is why we don't just run the geoscheme in the future with the future climate conditions?
Yeah, I mean, that would be the alternative approach. And I don't think geoscheme would be the best model for that, but you could use global climate model output. Like, these are these chemistry climate models where you have more detail on pollutants and air quality, species, so like PM. And so the alternative approach would really to do kind of take as much output from these chemistry climate models, which is already available, and compile that and then do kind of an ensemble approach and look at how PM2.5 changes in different models. And I think that would be quite interesting to compare against our approach. I think the advantage is, I think the disadvantage, let me say, of that approach is that the chemistry climate models never have the level of detail that we have in terms of air quality. I mean, just in terms of the different types of PM, like CAN, ESM, it's like the types of PM, I mean, this is getting into the chemistry. I mean, it's like there's basically black carbon, organic carbon, and sulfate. And we know, in fact, there's like probably dozens of components of PM that's captured in geostat. So when you do that approach, you lose some of the chemical detail. The other disadvantage is, in the chemistry climate model, once the PM is emitted into the air, it becomes sort of anonymized. So there's like no information about source. So looking at transboundary contributions is impossible because you don't know where the PM2.5 came from anymore. That being said, I mean, I would, if I had another, $60,000, let's say, it'd be great to have someone who would go through all the chemistry climate model data and look specifically for Canada, what those projections are in the future, and like maybe even make a website, that says, okay, for SSP, this SSP scenario and that SSP scenario, what are the different levels of PM2.5? I think that'd be excellent. I think there's disadvantages, that's why we use the emulator approach, but I still think using the climate model output would be super interesting. Good idea. Just gonna find money to do.
Merci beaucoup. C'est tout le temps qu'on a pour ce premier webinaire. Merci encore à Patrick et les gars.